we were discussing deformation, and now we will consider the propagation of acoustic waves in material medium. We know that when an acoustic wave travels through a medium, it creates a periodic deformation in the form of compression and rarefaction, and this deformation we have seen that it consists of the strain and the rotation of the elements of the material, and this would be represented by the strain matrix and a rotation matrix. The strain matrix again consists of the normal strain and the shear strain, that is the transverse strain. So, in that light we will now discuss the propagation of acoustic wave and the analysis regarding that how this elastic deformation creates that tensile and shear strain. We will consider longitudinal acoustic wave and followed by transverse acoustic wave in the light of the strain and rotation tensor element, how they are changing, I mean how they come into play for the case of longitudinal acoustic wave, and also unpolarized shear wave. We can also we will see in the later occasion that how a polarized shear wave can be analyzed, and the wave while propagating in the medium creates periodic deformation, and this periodic deformation will in turn produce a periodic change in the refractive indices. We will consider that, and that periodic change in the refractive index depending on the amplitude of the acoustic wave and depending on the frequency, the wavelength of the acoustic wave, that will be taken up to discuss this diffraction of light in the case of two different situations. We will discuss that Ramannath diffraction and Bragg diffraction. So, let us consider the elastic deformation. Once again, that mechanical strain associated with this elastic deformation is of this form S I j, this matrix which has elements del u I del j plus del u j del I. This element is the creates that 9 component deformation strain matrix. So, the strain tensor, this explicitly writing with all the components, this can again be written as del u 1 del x 1 plus del u 1 del x 1 half of that. So, that is put together, it gives you this. So, the diagonal elements are this, which correspond to the normal strain, whereas this off diagonal elements, they correspond to the shear strain. So, this S I j, how they are coming into the picture in the case of acoustic waves. We will see diagonal elements of the strain elements, these are represented by S x x, S y y, S z z, and the shear strain elements, they are represented by this, that is del u x, del y, del u y, del x, and so on for S y z, S z x. Okay. Importantly, this tensile strain, this is a consequence of longitudinal wave propagating, longitudinal acoustic wave propagating in the medium. That is what I mean to say, that when a longitudinal wave propagates in the medium, then it creates this tensile strain, and if a shear wave is propagating in the medium, that is a transverse wave is propagating in the medium, it creates this transverse, that is the shear strain. So, depending on what kind of acoustic wave is propagating in the medium, material medium, we will consider which elements of the strain matrix will be excited, and that will in turn create the periodic change in the refractive indices. So, this antisymmetric rotation tensor that is also associated with the deformation is written by this. You can see they are antisymmetric, because del u 1 del x 2 minus del u 2 del x 1, it appears here in the reverse order. So, this minus this. So, if I call this is equal to 2 3 2 1. So, that is y x y. So, this is your theta z. So, this is equal to minus theta z. Of course, this is infinitesimal rotation. So, this is delta theta z, this is minus delta theta z, and so on. So, they are antisymmetric, you can see from there, and interestingly, because the difference of these two terms del u x 1 del u 1 x del x 1 minus del u 2 x 2. So, this will correspond to this diagonal elements all 0. So, that is always true, that all the diagonal elements in the rotation matrix will be equal to 0. So, in a rotation tensor which is symmetric, we have all the diagonal elements equal to 0, off diagonal elements are of this form, they are antisymmetric. So, we can represent them. Now, we will consider the propagation of an, because having known this fact that the propagation of an acoustic wave will be analyzed from the point of view of these rotation and tensile strain matrices, we will consider the propagation of a longitudinal acoustic wave in a medium. So, let us first consider that any acoustic wave can be represented by plane acoustic wave can be represented by k dot r minus omega t. We know that this is the form of a plane wave, we have learnt, we have discussed that also as well, where k is the propagation vector and this capital omega is the frequency of the acoustic wave. So, a longitudinal acoustic wave which is travelling along x direction will create say periodic, because it is longitudinal, will create a periodic compression and rarefaction in the medium. As a result, the medium will be deformed all along the length of the propagation of the acoustic wave. We can represent this k equal to k of x, where k is the magnitude, and the deformation u can also be, this is a vector u, which can be represented as u of u and x unit vector. So, only tensile strain and there is no rotational strain in this case. So, we can analyze this situation considering that only this S x x is not equal to 0 and all S I j elements are equal to 0 and also the rotation elements are also 0. So, we have out of this 9 component strain matrix only one component S x x is non-zero. So, a longitudinal acoustic wave travelling along this x axis will create only this S x x element of the strain matrix. So, this is because most of all the other elements are 0. So, I have only S x x. So, let us put this S x x into the wave equation. So, in the case of so this is the situation for the longitudinal acoustic wave, whether the wave is propagating along y axis or it is propagating along z axis. In those cases, we will have only S y y or S z z. So, this is very straightforward, that one of the elements in the case of acoustic wave travelling in the a longitudinal acoustic wave will be exciting, that is S 1, S 2 or S 3. If we consider the transverse acoustic wave along x axis along this x direction, then we can write this propagation vector as k magnitude and k unit vector, but because we are not specifying that whether this acoustic wave transverse acoustic wave is polarized along y direction or z direction, because if it is propagating along x, then it can have two polarization, one is along z and these are the two pure transverse polarizations. We have seen that, and in that case u x equal to 0, but u y and u z they are not 0, they are non-zero elements, but because it is not longitudinal. So, this s x x, s y y, s z z, these elements are also identically 0, but s x y is equal to s y x, these elements are non-zero, these are also non-zero. That is a consequence of this, because in this direction and in this direction there is a compression and rarefaction. So, this and r x, r x y, r y x, they are also not equal to 0, and because these are the consequences of this del u 1, del x 1 and so on. So, in the case of a transverse acoustic wave, we can see that these elements s x y, s x z, y z, y x and z x, and similarly these rotation vectors, they will be present for to represent the acoustic wave's amplitude. So, in the case of longitudinal, we will now see the specific cases that a longitudinal acoustic wave which is travelling along x axis, it can be represented in general, it can be represented by the amplitude will be represented by u x, u y and u z. So, but for this case u y is equal to 0, u z is equal to 0, but u is only equal to u and unit vector. So, this is the only amplitude for the case of longitudinal wave along the x direction, and the direction of propagation will be represented by this. So, this is again so using this we can write the acoustic wave equation, this one, this will transform to this form, that now because this is your amplitude u x 0 cosine of k dot r minus omega t, or we can write this equal to k x minus omega t, because now k dot r is simply k into x, because the direction of propagation and this propagation vector there, the dot product of this, it is just simply the product of these two quantities. For the longitudinally polarized complete waveform, so we can write in this way that this equation can be simply rewritten as this, where we have replaced this by the amplitude a and this cosine of this argument. So, the diagonal elements of the strain for this case, because we are now considering the wave propagating along x axis. So, it will create only S 1, that is S x x, this tensile strain element, and u x will be represented by this diagonal elements of the strain tensor S x x is equal to del u x del x. So, I just have to take the differentiation of this with respect to x, which will give me this form. So, this S x x is nothing but S 1, which can be represented as S 0 or S 1 0, whichever way we would like to represent, but S 2 and S 3 they are 0, because u y itself is 0, u z is also 0. So, we can see that S 1 is only the non-zero element, rest the other two diagonal elements are 0, and in the same way for off diagonal elements S 4, this quantity, because u y 0, u z is also 0, and similarly for S y z, because these two are the same quantity S z y and S y z, and similarly for S 5, which is S z x, it involves u z which is equal to 0, but there is no change of u x along z. So, this quantity is also 0, u x along z there is no change. So, that is equal to 0. Therefore, this is also equal to 0, and for this u x again along y there is no change, because any change in u x is along x axis. So, this quantity is 0, but u y itself is 0. Therefore, put together this quantity is also equal to 0. Therefore, S y x or S x y they are also 0. We see that S 4, S 5, S 6 all the up diagonal elements are 0, and we have seen that the 2 other diagonal elements are 0. So, out of the 6 elements to represent the 9 component tensor, that only the S1 is the non-zero element. Therefore, it is now very straightforward to, and for the rotation matrix Rij, this quantity, all diagonal elements are identically 0. This is true for all rotation matrix, and for the up diagonal case you have this R y z is equal to 0, because u z and u y they are also 0 individually. As a result, this is equal to 0, and u del u x del y, this just now I mentioned that this is also 0, because there is no change of u x in the y direction. So, this is also 0, because u y is 0, and likewise all the other elements are 0. So, we see that the diagonal elements are 0, R 1, R 2, R 3, and R 4, R 5, R 6, all of them are identically 0. So, the only non-zero element out of these two tensors is the S 1 matrix, which is S 1 component of this tensile strain matrix, which is S 1, and you have seen that S 1 is del u x del x, that is the change in the displacement in the x direction per unit length. So, this is the strain, and the amplitude of this strain is represented by this. This is the amplitude of the strain. So, for the case of longitudinal wave, we see that this equation is very straightforward. You have only one element, and we will have to work with only one element to see how this S 1 changes the refractive index in the medium because of the periodic compression and rarefaction, which is which has a periodicity given by this propagation constant k, which is equal to twice pi by lambda. This capital lambda will be the periodicity, and the periodic change in the refractive index will propagate with the wave with a frequency omega. We will see that. Now, transverse or shear acoustic wave traveling along the x axis. So, this is the second part. The first part was that the wave was traveling in the longitudinal direction, and now this wave is traveling in the wave is traveling with this the transverse acoustic wave, that is a shear wave. So, it's the medium is now compressed and rarefied only in the transverse direction. The particles are now vibrating along this direction. So, it can have two independent polarizations, that is the vibration is along y axis, and then it is called the y polarized shear wave or y polarized transverse wave, and if the vibration is on the other hand along the z axis, then it is called z polarized. So, we will use this y polarized and z polarized this nomenclature to represent the propagation of shear waves in the material medium while discussing the deformation and optical interaction. Okay. So, for a transverse or shear acoustic wave along x direction analytically, because these are the complete general representation for the vector u, which has the component u x, u y and u z, but in this case because the wave is traveling in the x direction. So, there is no, so u x is equal to 0, but u y and u z they are the non-zero quantities. They are the non-zero quantities. Of course, this means that the wave is now unpolarized, because you have the polarization, both the polarizations are existing. So, for unpolarized shear wave, we can write this u, the amplitude of the deformation by u, and the direction of the wave propagation is along x. So, we will use this in the wave equation, in the equation of the acoustic wave. So, u will be represented by j of u the y amplitude and k u z 0, that is the amplitude of along the z axis. So, this is the two components of the shear waves which is travelling along the x axis, which is very clear. Okay, so, in this case we will analyze the diagonal elements of the strain tensor S x x is equal to 0, because u x is equal to 0, and del u y del y, this quantity will be also 0, del u y del z. So, this strain is also 0, but del u z del z, this is also 0. So, you have all the S 1, S 2 and S 3, all the 3 elements, diagonal elements of the strain matrix which correspond to the normal strain, they are equal to 0. The tensile strain part is equal to 0, but we will see that the shear strain, they are non-zero. Selectively for S 4, you have del u y del z del u z del y, this quantity is equal to 0, and S z x del u z del x plus del u x del z equal to this is non-zero, because we are looking at the changes in the deformation along the x direction. So, therefore, these quantities are now non-zero. So, therefore, you have S x z is equal to S z x, that has a finite value, and similarly for S 6, which is represented by this S y x, is given by this one in a similar way. Therefore, we see that S 4 is 0, but S 5 and S 6, they are non-zero. Interestingly, they involve z and x, x and y. X is the direction of propagation and z is the polarization. Similarly, x is the direction of propagation and y is the polarization. So, these two terms are surviving because of the x propagating wave with z polarization, x propagating wave with x polarization. Therefore, these two terms are non-zero. So, they will, and then the diagonal elements of the rotation tensor, they are always 0. We know that R 1, R 2, R 3, they will be in any case, because it is the difference of the same element from the same element. So, this is 0, and the off diagonal elements of the rotation tensor, in this case when you have both the polarizations present, that is y and z polarized shear wave, in that case you have R y z, y and z, because they involve displacement along z and displacement of u z component along y. So, that is equal to 0, but this R z x along x there is a displacement which will be equal to this, and along y there is a displacement with respect to x. So, that is non-zero. So, this quantity is positive. So, this is because of this. With respect to x, u y is non-zero, but with respect to y, u x is 0. But in this case, with respect to x, u z is non-zero, but with respect to z, u x is 0. So, this quantity is 0, here this quantity is 0. So, it gives you, because of the differentiation, you get a minus sign, and because of this minus sign and the differentiation, it put together, it becomes a plus sign. So, this is how we have R z x and R x y, these two are the non-vanishing rotation matrix elements which will be present. So, we can see that all the diagonal elements are 0. In the case of for the case of strain matrix, we have all the diagonal elements are again 0, but only this S 5 and S 6, they are non-zero, and in the same way for rotation matrix also R 5 and R 6, they are non-zero. So, we have this summary that for the case of x propagating transverse shear wave which is unpolarized, that is which has both x polarization, y polarization and z polarization components present. In that case, the deformation will be represented by this S I j and R I j matrices, strain and rotation matrices. Here only the shear strain components will be there, but no longitudinal components, and in this case only these rotation elements will be present. So, if we consider the only the strain, because in throughout all our discussion we will not consider the effect of rotation. So, for this particular case S 1 del u x del x will be given by this, that is for S 1, and for S 5 S 6 we have seen how the values will be taken up. So, this is S 1, in this case it is 0, but for the longitudinal case, this is non-zero, del u x del x, this is the non-zero element. For the x propagating transverse shear wave, so we have the summary that S 5 is equal to this, S 6 is equal to this, but R 5, you know, these are antisymmetric rotation matrix elements. So, this is minus, here R 6 this is plus, and then we will see using this polarization of the shear acoustic waves how these elements modify the impermeability tensor, and this impermeability tensor in turn then modifies the optical properties, which is manifested by change in the refractive indices in the three mutually perpendicular direction depending on the nature of the acoustic wave, particularly the orientation of the acoustic wave and the elements of the acousto-optic tensor, photoelastic tensor. So, in presence of the acoustic wave. So, these things we will discuss, we will pick up individually or the effect of a longitudinal propagation, longitudinal acoustic wave propagating in the medium. Then what will be the changes in the refractive indices, we will clearly identify that. Then we will consider the propagation of a shear wave. No, of course, before that we will also consider a longitudinal wave which is propagating along y direction for a given material, depending on the properties elements of that material, how the refractive indices change, that also we will see, because this might be useful in configuring the devices for a required change in the refractive indices. Then we will consider the propagation of acoustic wave, shear acoustic wave in a medium with y polarization and z polarization when it is propagating along x direction and so on. So, this is, and then we will see how these refractive indices are changing periodically. The change is also travelling in the medium with the speed of the acoustic wave. So, in the present discussion we talked about this acoustic wave and we connected with the elastic deformation, then tensile and shear strain components, which of the elements will be active for a given direction of the acoustic wave and nature of the acoustic wave, whether it is a longitudinal wave or it is a transverse wave. Then we also analyzed the which of the strain and rotation elements will be taking part for the case of longitudinal acoustic wave and transverse wave, which is unpolarized shear waves. So, we will continue with that in the next section. Thank you.